DSLAM. A DSLAM, Digital Subscriber Line Access Multiplexer, is a critical network device that acts as a bridge between multiple individual DSL subscribers and the Internet Service Provider's ISP core network. Think of it as a massive funnel located at the telephone company's central office or in a neighborhood street cabinet. It gathers data from hundreds of individual copper phone lines and merges them into one high-speed fiber optic connection. How a DSLAM works. To understand a DSLAM, it helps to look at the journey of your data. 1. From your home, your DSL modem sends digital signals over your standard copper telephone line. 2. At the DSLAM receives these signals from you and hundreds of your neighbors. 3. Multiplexing, the DSLAM multiplexes, combines all these individual low-speed streams into one high-capacity uplink, usually fiber optic or a high-speed ATM/Ethernet link. 4. To the Internet, this aggregated data is then sent to the ISP's core network and out to the global Internet. Key functions aggregation, its primary job is to collect traffic from many subscribers so it can be handled efficiently by the ISP's main routers. Signal conversion, it converts the electrical signals coming from your copper phone line into digital data packets, like Ethernet or ATM, that the rest of the Internet uses. Distance management, DSL speed is highly dependent on distance. The DSLAM is often moved closer to neighborhoods, in remote terminals, to shorten the copper wire length and provide faster speeds like VDSL2. Traffic management, modern DSLAMs, IP DSLAMs, can prioritize certain types of data, such as ensuring your Netflix stream doesn't lag while you are also downloading a large file. DSLAM versus DSL modem. It is common to confuse these, but they sit at opposite ends of the wire. DSL modem, located in your home. It talks to only one device, the DSLAM. DSLAM, located in the service provider's facility. It talks to hundreds of modems simultaneously. Types of DSLAMs. 1. ATM-based DSLAMs, older technology that uses asynchronous transfer mode to move data. They are less efficient for modern web traffic. 2. IP DSLAMs, the modern standard. They process data using Internet Protocol, IP, which is faster, supports higher bandwidth, and integrates more easily with modern fiber optic backbones. DSLAM architecture. The architecture of a DSLAM is designed for high-density aggregation. It is essentially a modular chassis, a rack, that houses several specialized cards to manage hundreds of individual copper connections and merge them into a few high-speed uplinks. The internal architecture can be broken down into 4 main building blocks. 1. Line cards, the mouths. Line cards are the interface where the physical copper wires from your home connect to the ISP's equipment. Port density, a single line card typically supports 24, 48, or even 72 ports. A large DSLAM chassis can hold many of these cards. Modem pool, each line card contains a bank of digital signal processors, DSPs, that act as the other half of your home modem. They handle the complex task of converting analog electrical signals from the copper wire into digital data. Service mix, modern DSLAMs are multi-service, meaning one chassis can house ADSL2 plus cards for long-distance customers and VDSL2 cards for nearby high-speed customers. 2. The backplane, the highways. The backplane is the internal wiring of the DSLAM chassis that connects the line cards to the control/uplink cards. ATM backplane, in older DSLAMs, data was moved internally using small, fixed-size cells, asynchronous transfer mode. IP/Ethernet backplane, modern IP DSLAMs use a high-speed Ethernet backplane. This is much more efficient for modern internet traffic because it doesn't have the overhead of converting data into ATM cells. 3. Control and uplink cards, the brain and exit. These are the most powerful cards in the chassis. They manage the entire system and provide the uplink to the rest of the world. Aggregation, they take the data from all the line cards and multiplex it into 1 or 2 high-capacity connections, usually 1 Gbps or 10 Gbps fiber. Traffic management, they handle quality of service, QoS, ensuring that time-sensitive data like a VoIP phone call gets priority over a background file download. Management, they provide the interface for engineers to remotely monitor line health, change customer speeds, or troubleshoot faults. 4. The splitter, the traffic cop, before the signal even enters the line card, it often passes through a splitter. Function, it separates the low-frequency voice, plain old telephone service, from the high-frequency data, DSL. Routing, the voice signal is sent to the traditional telephone switch, PSTN, while the data signal is sent to the DSLAM's line card. Summary, data flow through the architecture. 1. Ingress, your data arrives at a line card port via copper wire. 2. Processing, the line card converts the electrical signal into digital packets. 3. Transit, the packets travel across the backplane, the highway. 4. Egress, the uplink card bundles your packets with your neighbors and shoots them out over a fiber optic cable to the core Internet. Further analysis. Analyzing a DSLAM, Digital Subscriber Line Access Multiplexer, from these 5 architectural aspects reveals how it functions as both a high-density modem bank and a sophisticated network switch. 1. Line cards, the subscriber interface. The line card is the physical point of entry for subscriber copper lines. Density, modern line cards are high density, typically supporting 24, 48, or 72 ports on a single card. Termination, each port contains a chipset that terminates the DSL signal. In modern IP DSLAMs, the line card is intelligent. It converts the incoming ATM cells, from older DSL standards, or PTM packets, from VDSL, into Ethernet frames right at the edge. Multi-service, a single chassis can often mix different types of line cards, ADSL2+, VDSL2, or SHDSL, to serve customers at varying distances. 2. Switch fabric, the data engine. The switch fabric is the internal switching engine that moves data between the line cards and the uplink modules. Non-blocking architecture, in high-performance DSLAMs, the switch fabric is designed to be non-blocking, meaning it has enough internal bandwidth to handle the maximum data rate of every port on every line card simultaneously without causing a bottleneck. Traffic management, the fabric doesn't just move data, it prioritizes it. It handles quality of service, QoS, by ensuring that triple play services, voice, video, and data, are treated correctly, for example, giving priority to a VoIP call over a file download. 3. Uplink module, the gateway, the uplink module, or network interface card, provides the high-speed connection to the ISP's core network. Aggregation, it takes the combined traffic from all active line cards and funnels it into a few high-capacity ports. Interfaces, modern uplinks typically use gigabit Ethernet, GBE, or 10 GBE fiber optic interfaces, using SFP/SFP+ transceivers. Redundancy, most enterprise-grade DSLAMs have slots for 2 uplink modules to provide failover protection. If one fiber link is cut, the other takes over instantly. 4. Management module, the brain, the management module acts as the control plane for the entire system. Configuration, it allows engineers to remotely configure port speeds, update firmware, and provision new customers via protocols like SNMP or CLI. Monitoring, it tracks line health, signal-to-noise ratios, SNR, and error rates for every individual subscriber. Authentication, it often works with the uplink card to handle DHCP option 82 or PPPoE tagging, which helps the ISP identify which physical port a customer is connecting from for billing and security. 5. Backplane and chassis, the skeleton, the chassis is the physical frame, while the backplane is the nervous system connecting all the modules. Chassis, provides the housing, power distribution, usually -48 VDC for telco standards, and cooling, fan trays. Backplane, a passive or active circuit board at the rear of the chassis. When you slide a line card into a slot, it plugs into the backplane. Bus speed, the backplane's capacity defines the ultimate limit of the DSLAM. A 100G backplane means the total data moving between all cards cannot exceed 100 Gbps. Summary table, DSLAM Components component role analogy connects to individual home copper the individual front doors to a line card wires. Building. Switch fabric directs traffic between cards. The building's elevator system connects the DSLAM to the internet, the main highway exit leading out uplink module backbone. Uptown. Management oversees system health and the building manager/security module settings. Office. The physical data path between all the internal hallway connecting all backplane cards. Rooms.